Stanford University.
Please join me in welcoming Sally Benson.
Thank you very much for that nice introduction. Okay, so now we're going to talk about carbon capture and storage. I've got a lot on the agenda today. First, for those of you who might not be so familiar, I'll briefly introduce what it is. Then second, I want to spend some time talking about why we need CCS. With all of the plentiful natural gas coming from shale gas, people are starting to say, well, gosh, maybe we don't need this after all. So I want to address that issue, what makes CCS an important component of the portfolio. Next, I want to talk about what's the global status of CCS. A lot's happened in 10 years, and I'd like to review that. And then finally, I'll briefly talk about some of the major challenges and R&D opportunities in this area. And at the very end, I'll briefly talk about some of the research that's done in my research group here in the Energy Resources Engineering Department. Okay, carbon capture and sequestration, sometimes also called carbon capture and storage, sometimes also called carbon capture and geological storage. Basically, the idea is that instead of letting carbon dioxide that's combusted in a power plant or an industrial process, instead of letting that go into the atmosphere, that you capture that and then sequester it. And I like the word sequester because basically what it means is to set aside or to basically prevent it from interacting, for example, with the atmosphere. So that's basically what CCS means. Now, in terms of the technology, how is it actually done? There are basically 4 steps. The first thing you need to do is you need to capture carbon dioxide, basically from the smokestack of a power plant or industrial process. And what capture means is typically the smokestack has, say, 85% nitrogen, maybe 15% CO2 for a coal plant. For a natural gas plant, it might be about 95% nitrogen and 5% CO2. So you want to separate the carbon dioxide from the other gases that are coming out of the plant, and that's called capture. The next step is to take that gas, carbon dioxide gas, and then compress it into a liquid, basically to make it more manageable so it's easy to deal with. The next step is to put it into a pipeline where you could then transport it to some location where it would be pumped underground for permanent sequestration in a rock formation. So those are basically the 4 steps. And briefly, I'll talk about some of the options for carbon capture. There are different technologies that are available. All of the technologies that I'm talking about are actively being employed to one degree or another, and also the subject of very active research programs. So the first is a technology called post-combustion capture. And the idea is that you have your fuel and you have air, you burn them. So this is the simplest kind of system. You burn fossil fuel in air. The mixture that comes out is nitrogen and carbon dioxide and water. And you use something called basically post-combustion capture. That you contact this gas coming out with a solvent, and then that solvent can be used to purify the carbon dioxide. So that's basically post-combustion capture. So you capture the CO2 after you've burned the fossil fuel. So here's actually a picture of a real post-combustion capture unit. This is a project in China, a small pilot test done by Huaneng Group, which is the largest electricity producer in China. And this was one of the first post-combustion capture pilots in the world. So sometimes we hear about, well, how much is China doing? Well, in reality, China is doing a lot in this regard in terms of technology development. And what you see are 2 towers. You have an absorber tower. And so in this tower, you have your flue gas going up through the tower. You've got your solvent dripping down through the tower. And by the time the solvent's to the bottom, you've removed all the carbon dioxide from the gas. You take that what's called a rich solvent and put it into another tower. You let that drain down and you have steam go up through it, and then you have steam and CO2 coming out the top of that, where you can then take that, what you first dry it and then compress it. So this is what one of these units actually looks like. This unit operates very well. The CO2 that is collected here is used to actually make dry ice in Beijing. Okay, so the next technology is something called Oxyfuel combustion technology. Here the idea is that you take air and you separate the oxygen, because it's oxygen that you need for burning the fossil fuels. You separate the oxygen from the nitrogen. And so when you go into your boiler, you just have a mixture of oxygen and your fuel. You might have some recycled CO2 to help keep it cool enough. And then after you burn this mixture of oxygen and fuel, you have primarily a mixture of water and carbon dioxide. So you basically do a separation before you go through your combustion process. So that's another way. That's called oxycombustion, and it's favored in some ways because this process here is very simple, and today we already know how to separate oxygen from air. That's a very standard technology. The final of the major options that are available today are something called pre-combustion capture. And here, once again, you start out with air. You separate the air into nitrogen and oxygen. You take the oxygen and the fuel and you put it in a gasifier, so you partially oxidize the coal. You turn it into something called a syngas, which is a mixture of CO and hydrogen gas. You put in some more steam and you further react this so that you end up with a mixture of basically hydrogen and carbon dioxide. And the hydrogen then can go on and be used in a combustion turbine, or you could also use the hydrogen for other purposes such as transportation, and then the separated CO2 goes on the pathway. So all of these are available technologies. All of them are being studied today. There's a race. Like if you favor one of these, you think your technology is the best. And you think all the rest aren't good, and so forth. So it's great that there's so much competition between these various pathways. Okay, so now we have essentially a pure stream of carbon dioxide. The next two steps are to compress the carbon dioxide and to put it into a pipeline. And I hope you can see this, but this is actually a real carbon capture facility. This is in Algeria, northern Africa. And there are the absorber towers here, and there are compressors, and this here is the pipeline which is running out of the facility, and it goes about 10 kilometers where then the CO2 is pumped underground. Compression is a very mature technology, as is transportation. In the US, there are over 2,000 miles of CO2 pipelines. This map shows a picture of them. You have sources of CO2, some industrial sources, such as these, some natural sources, and these are all pipelines that primarily take the carbon dioxide from these sources to oil fields where the carbon dioxide is injected underground for enhanced oil recovery. But the main point of this is to point out that we do a lot of carbon dioxide transportation and pipelines today, about 50 million tons per year. So again, a mature technology. So finally now moving on to geological storage and options for that. The CO2 is pumped deep underground. So when we say deep, we're talking about, think about a mile or a kilometer, either one. They're not quite the same, but that gets you in the right ballpark. And we can take the carbon dioxide that's now compressed liquid and inject it either into depleted oil and gas reservoirs. That makes sense because we've actually extracted fluid, so why not try to fill some of that pore space back up with CO2? In some cases, actually in most cases, the oil reservoirs aren't actually depleted. In fact, that there's oil or gas or oil and gas left, and it's possible to significantly increase the recovery of that residual oil by pumping CO2 underground. So there's lots of interest in this. It's called CO2 enhanced oil recovery today, and I'll say more about that. The next option is to put the carbon dioxide into what are called saline formations. These are rocks filled with salty water. So think of like a sandstone rock, like think of compressed beach sand, and the water, the pore spaces are filled with very, very salty water that isn't good for drinking. And then the final option is that you can put carbon dioxide into coal beds. And here a different process takes place, that the carbon dioxide actually attaches itself chemically to the coal and basically gets stuck on the coal. So those are the kind of options that are being investigated and pursued today. Okay, so what happens when you put the carbon dioxide underground? So it's a liquid when we first start pumping it underground, but it's a liquid that's actually buoyant, or it's less dense compared to water. So we'll run this again. So, and because the carbon dioxide is lighter than water, it wants to float. It wants to float up towards the ground surface here. However, we would only consider putting carbon dioxide in geological formations where there's something called a seal. And a seal is a very fine textured rock with tiny, tiny pore spaces that preclude the CO2 from entering in it. So it basically provides a cap rock or seal that traps the carbon dioxide underground. And again, it's very deep. It's at least 1 kilometer deep. So that's basically, in a nutshell, how it works. So the question is, well, have we done this at all? I talked a little bit about CO2 enhanced oil recovery, which we've certainly done, but what about CO2 sequestration in saline aquifers? And the most known and notable of all of these sequestration projects is the Sleipner project in Norway. So here's the coast of Norway, and this is the North Sea. And there's a very, very large subsea saline aquifer called the Utsira Formation that's shown here. And so in 1996, the Norwegians wanted to develop another gas field. They have lots of offshore gas. But there's also a tax in Norway that if you emit CO2 into the atmosphere from an offshore platform, you have a tax of $50 per ton. So this was going to be very expensive if they produced this natural gas, which naturally had some CO2 in it. It had about 10% CO2. So you can't sell gas like that. You have to process the gas or clean it up by removing the carbon dioxide. So if they wanted to just take that carbon dioxide and emit it to the atmosphere, they would have had to pay a lot of money in taxes. So they said, well, why not sequester the CO2 underground? Hence, it became the first really intentional carbon sequestration project. Here's a picture of the offshore. This is the platform from which both these gas-producing wells as well as the sequestration well are located. And here's actually the offshore CO2 separation platform. So this project was about 1 million tons per year. So you're probably wondering, is this a big number? Is this a little number? Think if you had a 500 megawatt power plant, this would be about 1/3 of the CO2 emissions from a 500 megawatt power plant. So it's a big amount of CO2, but it's not huge. But it's big enough to be meaningful in terms of our ability to understand whether these technologies could be deployed more widely. The thing that they did that was really fabulous from this project is they began to do a lot of seismic monitoring. So seismic monitoring, you can kind of think of it like as a sonogram for the Earth. So you basically pass sound waves through the crust of the Earth, and when they encounter a material that has very different properties, the sound waves basically bounce off that interface. So they've been doing this now since even before there was injection, and they continue to do it today. And what they showed is it's really easy to track where the CO2 is going. So this was before there was any CO2 injection at the site. This is a plane through a slice through the Earth. You can see what was the top of the Utsira Formation and the bottom. And if you look at a map view, nothing much happening. Here's 2001, so they've been injecting now for 5 years, and you can see radically different kind of situation than you can see here. And all of these individual layers are interpreted to be thin layers of CO2 trapped beneath a thin shale layer within the Utsira. You can see the footprint of the plume, and as time goes on, you can see the footprint grows, which is what you'd expect because you're pumping more and more in. And you can see again from these cross sections it's growing. And very importantly, if you look above the storage reservoir in the seal, you don't see carbon dioxide. So this was the first of these large-scale projects with lots of monitoring data that was also available to scientists from around the world to take a look at it. Okay, so that's the background. So now what I want to talk about is why do CCS? If we talk about wind power, well, there are lots of reasons to do wind, right? It provides another electricity source. It can help with, energy security because it's something, made on U.S. soil, for example. But why do CCS? Well, there's really only one reason to do CCS, and that's because we don't want carbon dioxide emissions into the atmosphere. So that's the sole purpose of this. It really is a climate change mitigation technology. So what we're trying to do is avoid emissions. So that's reason number one. Number two, so CCS, it also turns out, is applicable to a lot of different emission sources. About 60% of all of the emissions are amenable, of global emissions are amenable to CCS. So if this technology can be developed for the power sector, then there's opportunity in the cement sector, gas processing sector, and so forth. So that's another reason. So in 2005, we surveyed all of these sources, and we identified 7,400 sources greater than 0.1 million tons a year, where potentially CCS could help reduce those emissions. So another reason why CCS is attractive is if you do a CCS project. So if we imagine a 1,000 megawatt coal-fired power plant, of which there are many, and we implement CCS with 90% capture, we're going to be reducing emissions by 6.5 million tons of CO2 per year. Okay, well, again, is that a big number? Is that a little number? Well, to put it in perspective, if we took 2.8 million cars, okay, so this is 2.8 million people needing to make a decision, and to shift from 25 to 50 mile per gallon car. Okay, so you get enormous leverage by doing one project with a small set of actors. You can achieve equivalent emissions reductions of 2.8 million cars each, basically going from maybe a pickup truck to a Prius. That's what we're talking about. So we can dramatically reduce the number of actors, which would, in principle, allow us to more quickly reduce emissions. Okay, so now I want to talk about natural gas. There's been a lot of enthusiasm and excitement about the discovery of the shale gas, of this resource that is available broadly throughout the United States. And we've developed technologies, this hydrofracking technology, which enable us to produce gas. And that's fantastic because what that means is that we are going to be able to have a stable natural gas supply for a long time. So this is some data. This is actual gas producing data from the EIA. Up until the actual data goes through 2010, and then projected out to 2035. And what you can see is this green wedge. This represents this shale gas wedge. So it's really very exciting. If we didn't have this, we would be in the situation where natural gas production would be declining. But instead, not only is it not declining, but it's actually growing significantly. And so just a couple of numbers I'd like you to focus your attention on. So about now, we're at about 21 trillion cubic feet of gas production. And if we look out to 2035, we're in the range of, say, 26 to 27 trillion cubic feet. So we'll come back to that number, which I'm going to refer to as the incremental gas production. Okay, so let's look at what we do with natural gas today. So this is in the United States. We have a total supply of 23.8 TCF. A small amount of that is imported. And today we use it in the natural gas industry for things like gas cleanup, residential for heating and cooking, commercial, again, heating and cooking, industrial applications, doing things like making fertilizer, and so forth. Very, very small amount in the vehicle fleet, and a significant amount, about 7.4 TCF in the electricity supply. So about 31% of our natural gas actually goes to produce electricity today. So what I would like to do now is ask the question, well, if we took all of that incremental gas, which is about 6 TCF, and we say that it won't be used for any other purpose, we're going to use it to generate electricity, how much coal could we stop using for power generation? Okay? And of course, the reason we want to do this is that the natural gas emissions from natural gas combustion are about half that of coal. So if we can switch over to coal, that means we can reduce the emissions by half for every kilowatt hour we produce. So that's why we want to do this. Okay, so our assumptions are that we have 6 TCF by 2035 that we're using to generate electricity. So this number's gone up from 7.4. And we're also going to assume that we have a power generation efficiency of 48.8%, which is significantly better than today's coal fleet, which is about 33%. And the 48.8% corresponds to what's a combined cycle gas power generator, or something we'd sort of use in a base load kind of mode. So if we took all of this, gas and produced electricity, we could replace about 45% of the existing coal-fired generation as compared to the 2010 baseline. So on one hand, that's absolutely great, right? That's a lot of emissions reductions we can achieve. However, it isn't going to be enough. When we think about 2030, 2050, we would like emissions, 50% emissions reductions, 80% emissions reductions. So emission reductions associated with this 45% aren't going to be enough. So arguments that say, well, let's sort of postpone focusing on CCS because we've got all this gas, I think are spurious arguments, because simply it isn't going to be enough. In addition, natural gas also has CO2 emissions, which eventually will need to be dealt with. So just one more point. So in this analysis, I've suggested that about 45% of our coal-based generation could be replaced. EIA predicts a maximum of 20% replacement by 2035, partially for economic reasons and partially because these other end-use applications also would benefit by more natural gas. Okay, so that's part of the natural gas story. So say we go down this pathway and we decide that we're really going to focus on natural gas. We have a very active, thriving coal industry in this country, very large coal. Wyoming is the biggest energy exporter to the United States that there is. So there's a big, big industry there. So the question is well, what's going to happen to that coal? And this is a picture showing the amount of coal use in various portions of the world. And really the big area to focus on is this big circle here, which is Asia. And you can see that over time, the amount of coal use in Asia has been growing very dramatically and in fact continues to grow. So the question is well, will the US become an exporter of coal to Asia? And in part, we already know the answer. What we have seen is an increase in the amount of coal exported from the US. That's shown here from the year 2000 up to basically 2010. And with some variability, but we see an increasing trend. This is exports to Asia. And in fact, if you look at the difference between 2010 exports and 2011 exports, the amount of coal being exported to China has doubled. So the idea that somehow we can have significant emissions reduction sort of by ignoring the fact that the coal is there and focusing on natural gas, again, I think is spurious. We need to make sure that CCS technology is available for all the people who are in a position where they think they need to use coal to support their energy systems. So anyway, just a note of caution. And then just finally, one more point along these lines is that there are many, many studies that people have done looking at emission reduction strategies, forecasting out to 2050, 2100, and so forth, looking at the portfolio mix of technologies that could be used to achieve large and rapid emissions reductions. And this is just yet another one of these. This was done by the IEA. Showing that these are efficiency reductions. These are associated with things like fuel switching. Here we have power generation efficiency and fuel switching, growth of nuclear power, renewables growing, and this wedge here corresponds to CCS. So yet another analysis which suggests that CCS is likely to contribute something on the order of 20% to overall emissions reductions. Okay, so that's basically that's why I believe that we need to keep our eye on the ball of advancing CCS technology. So I'd like to say a little bit about the global status now. This is a chart that shows 8 projects around the world which self-identify as CO2 capture and storage projects, mostly in the United States, some in Norway, some in North Africa, and so forth. And there are a couple of things that are worth noting. That if you add up this total list, it's about 20 million tons per year of CO2 emission reductions associated with this. Second observation, very important, is all of these projects are associated with industrial sources. Not a single one of these are associated with power generation. And at the end of the day, if CCS is going to make a big impact, we have to start thinking about capturing and sequestering CO2 from electricity generating sources. The reason that we see this associated with gas processing and fertilizer manufacture is it's much less expensive to capture CO2 under these circumstances. And then the final observation is if we look at where the CO2 is going, 5 of the projects put the CO2 into oil reservoirs for enhanced oil recovery. People can make money that way. But 3 of them, on the other hand, are purely saline injection projects with no purpose other than to eliminate emissions of CO2. So that's what's happening today. There's an institute called the GCCSI, the Global Carbon Sequestration Institute, and they track worldwide all of the projects, and they bin them into a number of different categories. The first category is identify. That means a company or a government has said, I am interested in doing a CO2 project, CO2 or CCS project in this location with this source, for example. So very, very early stages. And today there are about 8 projects under that category. The next step is to evaluate, meaning where would you consider putting the carbon dioxide, what kind of capture technology you might use. So basically a scoping study. So that's an evaluate stage. The next stage is you've said, well, you know, I've evaluated this, it looks pretty good, therefore I'm going to actually go into active project design and really try to start pinning down costs and so forth. The next decision is to move on to the execute phase, and that means you start construction. So you've made the big investment decision, you're spending the billions of dollars, and by this point, these people are really committed, and then these are the operating projects that you've seen. So you can see that there is a pipeline of projects coming along, but there's been a lot of concern that due to the lack of firm commitments to reduce CO2 emissions, that this pipeline is basically going to begin to dissolve and fall apart. But before we get to that briefly, we can look at, well, what if these projects did come to fruition? What if that whole pipeline panned out like we anticipated, or like the initial scoping studies suggested it might? So what this would show then is the CO2 emissions reductions as a function of time. And so this corresponds to the operating projects today. This corresponds to those projects that were in the execution phase, meaning they're already doing the construction. So if these projects continued by the end of the decade, we'd be about 33 million tons. And then there's a lot of other projects here, which if came to fruition, would lead to more than 100 million tons per year. Now, the track record suggests that the attenuation in these is going to be extreme. And if even 20% of these projects came to fruition, that would probably be a good compared to the current track record. So today, we're really on track, certainly for this 33 million tons, but the rest are more uncertain. So I mentioned that there was concern about attrition of these projects, and again, this group is tracking these. So in 2010, there were 77 in the pipeline. 3 have been canceled, 8 have been put on hold. On the other hand, 8 have also been added, so we're sort of at a net of down 3 projects in that CCS pipeline. So certainly it's not growing, but it's only shrinking slightly. So this will be the last part of this discussion about the status, and it's sort of the good news, bad news story. So beginning in about 2005, 2006, governments started really becoming interested in CCS. And around the world, there was a very large commitment to invest in CCS through things like I was going to say loan guarantees. I guess that's not a really great word these days. But yes, things like loan guarantees, pilot projects, demonstrations, R&D, and so forth. So globally, about $23.5 billion was committed. That's very, very sizable. And as a consequence of this, there's now a very large R&D, vibrant R&D community working on everything from nanoscience to geologic characterization, working on various aspects of that. So that's fantastic. That's really emerged in the last 5 years or so. In terms of industrial sources, there's been a lot of interest in like ethanol plants have actually a pure stream of CO2 that comes out of them. There's been an interest in taking those sources of CO2 and sequestering those, partially because they're easy and it's low cost. You've already sort of spent most of the money, but in some cases driven by the opportunities for EOR, because with the very high prices of oil, EOR is quite attractive today. Another set of good news is if I were up here like 4 or 5 years ago, I would say that we don't have regulations. Around the world, there are not the appropriate regulations that govern how do you do accounting, CO2 accounting, or which sites would you be allowed to inject CO2 in, and what kind of monitoring and so forth. But in the major areas of interest, so Australia, Canada, US, Europe, there are basically laws now that govern how CCS could be implemented. And then finally, some real progress recently is that it's been determined that CCS could actually become part of the clean development mechanism. It was prior to that precluded from that. So this is kind of the good news. On the downside, as the years have gone on, in 2008, I think everyone thought that we were going to have a climate policy and there were going to be mandatory, emissions reductions. And the industry I deal with, we're all, marching along that pathway. But as time has gone on, the commitment just appears to be weaker and weaker. And so the industry has found it hard to sustain the level of investment that we need in order to develop this technology on the time frame that would be meaningful. So a second part of that, though, is that when the engineering studies have been done on capture units in particular, the cost came in much higher than the earlier estimates. Part of that is due to real inflation that occurred during the middle of the 2000s. Part of it has to do with the fact that there's not a supply chain developed for CCS components. And so projects were coming in 50%, 100% more than anticipated, and that's a real project killer. And then finally, in Europe in particular, in the Netherlands and Germany, the local citizenry near prospective projects have basically not been happy with the idea that there would be a CCS project. They felt it was too risky. And consequently, several projects have actually been stopped because of local opposition. So it's a mixed situation. You know, some good things are happening, but the future is not all rosy. So thinking now about some of the major challenges for the future. I mean, you could write a really long list. I decided to write a short list. The first thing is, if this technology is going to be implemented on a large scale, it would be extremely helpful if the cost of capture were cut significantly. So that's the first thing. And the second is we need to increase the confidence in the safety and permanence of CO2 storage. So those, I think, are the two big challenges, and I'll just say a little bit about them. So in terms of the cost of CCS, most of the cost is capture. About 75% is capture and compression, maybe 15% associated with transportation, and about 10% on the sequestration side. So when we're talking about cutting costs, what we're really talking about is cutting the cost of capture. And I think that point will be brought home by looking at this chart, which has a variety of technologies. Here's geothermal, here's hydropower, wind, nuclear, biomass, CCS on coal. We have CCS on gas over here, and then we have solar PV and solar thermal and solar PV. And these two boxes are for CCS with coal and gas. And on this axis, we have the dollars per ton of CO2 avoided. Okay, so that means if you want to cut back on 1 ton of CO2 or reduce emissions by 1 ton, that, for example, for coal, that's going to cost you anywhere from, say, $60 to $120 per ton. Okay, and then we can compare that to these other technologies, and clearly what you see is that CCS is not the low-cost technology. As a matter of fact, it's fairly far up, and only the solar technologies are really more expensive. So this is the challenge, is to reduce those costs. So what are the R&D opportunities? There's a lot of fantastic material science, chemical engineering going on to find ways to more efficiently take the CO2 out of a gas stream. There are better solvents. I talked about the post-combustion capture and the use of those solvents. So basically new materials. Also geometry. How do you make your design more efficient so you can get even better performance for the same kind of sorbent capacities? Another idea is to use membranes. Membranes have the advantage that you don't have to drop the pressure so much. And so when you recompress the gas, you don't have to use so much energy. There's also the possibility of solid adsorbents, where the CO2 attaches itself to a solid surface, which you can then later desorb the CO2. And then finally, system integration. So at GSEP, we have just started some new capture projects, and 3 of them are shown here. One of them is something called ionic liquids. They're basically an alternative to the current solvents. These are basically salts that are liquid at ambient conditions, and it turns out that they're really good at dissolving CO2, and it takes less energy. A second approach we're looking at are using something called metal organic frameworks. These are materials with remarkably high surface area that can adsorb CO2. But one of the problems with them is that if there's water present, they also adsorb water. And once they do that, then they're inefficient for CO2. So the idea is to basically make a hydrophobic coating around one of these metal organic frameworks so that it would repel water but still retain CO2. And then the last idea is to basically mimic what goes on in biological systems with carbonic anhydrase to try to take advantage of those the enzymes that do that to efficiently both capture and release CO2. So those are just some of the research ideas. So now just quickly moving along to the storage side. So and here I'm going to talk about what we do in my lab. When you put carbon dioxide deep underground, say a mile underground, it's really hard to really see what's going on, right? We have seismic imaging, which is fabulous, but the spatial scale where we can make those observations is sort of on the order of tens of meters or maybe even larger. And in fact, what we would like to do is be able to take a really detailed look and so make sure that we understand the physics of what happens when we put CO2 into rocks. So in my lab, what we do is we take pumps and heaters, and we put rocks into these core holders which can withstand very high pressures and temperatures, and we basically subject the rocks to the kind of conditions that they would have underground. And then we pump carbon dioxide and water and salty fluids through the core, and then we use a medical imager to look what happens inside those rocks. So early on, when we started doing these experiments, we found out that whenever we put carbon dioxide into a rock, that what we found is that we could never get a uniform distribution. So the green is where the CO2 is, and you can see it's really patchy and it looks strange, and we didn't understand why. We could also look at other properties of the rocks. This is the porosity, so the fraction of the rock that actually can contain CO2. And basically what we found out, it was sort of the details of the geology or the heterogeneity that was controlling this. But there really wasn't a good theory or a way to study this, so my students, my very brilliant students and postdocs, have over the years really done a tremendous amount of work in this area, and sort of highlighted here. The first one is to make these medical scans quantitative so that we could really say, well, the saturation is 22%, not 30%. The next thing we needed to do is we needed to figure out how to assign a property called the permeability to the rock inside the core. Nobody had ever done that before. And Mike Krause, who is here, did a really fantastic and creative job at finding a way to describe the permeability. We then needed to develop a theory that would take this information from these scans and from this permeability to quantitatively relate the properties of the rock to the saturation of CO2 or the fraction of CO2 in the pore spaces. And then finally, in a typical rock, there might be a million different pixels with all different properties, and so you can't just write down an analytical solution. You have to use numerical simulation, and it turned out it was very intractable to even do relatively simple problems. So Boshao Lee developed a very, very efficient simulator, so we can now handle these problems. So this is just an example of where we've come from, sort of looking at those rocks and going, oh, gee, how come it's not uniformly distributed? Here's a comparison between experimental results showing a wide range of saturations in the rock. Here's just one of the slices. And these are actually now our numerical simulations combining the theory and the quantitative measurements. And you can see that the comparison, our ability now to really say that we've got the physics right, has made tremendous advances. And at least for me, it gives me a lot of confidence that as we move to the scale up, that at least we've got the very foundations, the fundamental foundations well described. Okay. So I'm not going to show you this because I would like to go to the concluding remarks. So So the first thing is that I hope that I've been somewhat successful in making the case that CCS is an important part of solving the global warming problem. It's needed for rapid and large emission reductions. It has the real benefit that a single project with a relatively small amount of actors can lead to significant emission reductions. And I like to think of this, sort of 1,000 megawatt power plants as 2.5 million cars, doubling efficiency. And finally, though, for all the great news about natural gas, which is really great news, it's not going to be sufficient, and we should not sit back and wait until all of that fuel switching plays out before we continue to engage in the CCS issue. Progress on CCS has actually been remarkably rapid. Back in 2000, almost nobody ever heard of what I didn't even know what CCS was. I think I learned in 1998. But now there are many industrial scale projects, a huge R&D community, and large government support to continue that work. There's still a lot of work to do. The cost of capture is really a significant issue that needs to be dealt with. And finally, with regard to sequestration, we still have a lot to do before somebody is going to say, yes, I'd be happy to have that project, under my farm, under my town. So we have to make progress there. And then finally, if there's one single thing that we really need to sustain progress, is we have to get serious about CO2 emission reduction mandates, because without that, we're not going to be able to sustain the industry investment, which is absolutely crucial to making progress. So with that, thank you. To paying for the capital cost, you're having to put a lot of money into the energy that's needed to capture the CO2. So it's really inherent to the problem why capture is more expensive. Yeah. Okay, how about right there? Yep.
Where does the lack of confidence in sequestration come from? What is it?
I think first that, a lot of people are just not familiar with the subsurface. Geology, I don't know how much geology is really taught in, middle schools now or high schools. So the idea that you have sort of a layer cake earth underneath you where you've got seals and reservoirs, and I think that there's just fundamental lack of knowledge. So I think that's number one. And then, I think people tend to be afraid of the unfamiliar. So I think it's unfamiliar. So as an example, natural gas storage is almost exactly identical to CO2 storage. And there are plenty of places where there are huge natural gas storage facilities, like under Berlin, there's one. And sort of people don't pay attention to it. So part of it's just the fear of the so I think those two things, sort of fear of the What's that?
Is it unfounded?
I think, well, if you select the site carefully, and you monitor, and you make sure your wells are constructed right, and you keep on top of you operate it safely, and a regulator has said, yes, you are doing all this stuff well, then I think it's safe, and then I think it's unfounded. If, on the other hand, some were to do these projects carelessly, there is big risk, yeah. How about back there?
Is the CO2 sequestered and stored subject to chemical changes that can put them back into the carbon cycle?
Mm-hmm. Yeah, so it depends on the type of rock. So if you have a rock that's mostly a sandstone, silicate, like quartz formation, the reactions will be extremely small. If, on the other hand, you have rocks like feldspar or basalt, those rocks can be more reactive. And in fact, there are people who are studying, including some in the row right here, studying how you could first understand and then harness those chemical reactions to convert the CO2 to a solid. There's also some concern that if in certain types of reservoirs that you could actually damage the integrity of the reservoir if you're dissolving, for example, carbonates, and you could maybe damage the seal. So it goes on both sides, but in many reservoirs, the conclusion today is that there won't be that much reaction. Let me see. Why don't we pick one over there, and then we'll go back over here.
Would something like a carbon tax be good for the CCS market right now, or is it still too expensive and unknown that would sort of force energy companies towards some of these alternative sources and sort of get rid of a lot of the need for CCS projects?
Right. I think a carbon tax would be good. I think something that signals a seriousness about reducing emissions beyond things like renewable portfolio standards. I think the California climate legislation is good and would be driving in that direction. So no, I think a carbon tax is good. It will be a long time before a carbon tax is high enough, before just sort of by penciling out the dollars and cents you do a CCS project. On the other hand, if you have an industrial source, like from a fertilizer plant, and there's an EOR project you can do, or maybe enhanced gas recovery, that might make sense today, and with, say, a $20 or $30 ton carbon tax, it would be an attractive project. So there's a range, but in general, it would be really good. Yeah. Yes. How about right there? Yeah.
So I'm curious, worst case analysis, and I've heard the whole town's being wiped out by volcanoes belching CO2. If you had a formation that looked good now, really porous, but was forgotten about for hundreds of thousands of years, and there's suddenly an earthquake that ripped it open, like what's the worst case as far as like the kind of layer of CO2 being cascading downhill?
Yeah. So the person who's done the most on that is someone named Karsten Pruss from Lawrence Berkeley Lab, and he tried to identify whether there were any sort of feasible eruptive scenarios, as opposed to sort of a slow seep that would come out. And the only scenario where he could generate an eruptive type of behavior is where the CO2 is very hot, like in a geothermal area. So if you had CO2 you put into a geothermal reservoir, that might have enough energy to cause an eruption. In terms of that kind of bad scenario, I think really it's more pipeline ruptures that you would worry about, and those need to be managed carefully. And and obviously we've seen evidence here that at least with our natural gas pipelines, they're not being as managed as carefully as we'd like them to be. But yeah, I think in terms of human impact, human health risk, I think it's pipelines that are the big risk. Yeah. Okay, maybe we'll go back over there, and then I think we're only going to do like two more or one more after you, and then we've got to go. Okay, yes, you.
Why is it so much more expensive to do CCS for natural gas? Is that a function of the size of the power plant typically?
It's because instead of having like 15% CO2 in the gas, you've got 5%. So you basically are trying to concentrate CO2 from a more dilute stream. Yeah. Okay, one more question. No? Okay, how about you? Yeah.
Is there a seismic risk? Like you have, they're discovering there might be things, but now they're doing fracking that might cause seismic events.
If there is a large pressure buildup in the storage formation, there is a seismic risk. How big the pressure buildup has to be to create a seismic risk is uncertain. And We do know locations that would be more risky. So if you have a tectonically active area, that would be a riskier place for earthquake generation. And there are people like Mark Zoback who study that depending upon the orientation of pre-existing faults and fractures, you'd be more likely to generate seismic events. So yes, seismicity is something that, number one, would be monitored in a project as microseismicity. And second, if projects where the pressure buildup is very high, I think are risky projects in that context. So I think that selecting sites where it's highly permeable, not injecting too much per well, will be important for managing seismic risk. Okay, all right, well, anyway, thank you. And
For more, please visit us at stanford.edu.